Hello and welcome. My name is Alberto Marquez. In this video, we will discuss the fundamental tools to model networks and how those are used to represent the supply chain network, how they are used to optimize it too. In designing supply chain networks, there are many factors that can influence the decisions that drive the design process of a supply chain network. These factors include expected delivery time, geographic area to cover, infrastructure available, demand distribution, transportation cost, and manufacturing and warehousing costs composed of labor, energy, and others. Networks can be represented in space by using graphs, and mathematically using matrices. Networks are representations of relations between discrete objects. Discrete refers to objects that can be counted. The discrete objects in the supply chain include sources, destinations, warehouses, routes, products, crews, etc. Networks are composed of vertices and edges. Supply chain networks can be used to represent many different processes within the supply chain. It can represent the flow of product, the flow of information, or the flow of cash through the different actors of the supply chain. Networks can be used to represent assignments of products to different manufacturing facilities, or available product to orders placed by customers. They can be used to represent which warehouses will cover which territory, etc. Given the mathematical nature of networks, different computations can be performed, like the total investment in setting up a particular network, the cost of operating a particular network that distributes product. Two different configurations of edges and vertices could have significantly different operational costs. That's why it is important to be able to optimize the return on the investment by investing in what is convenient for the goals of the organization. It is also important to take into consideration the capacity to respond, the operational cost, and the resilience of the network, all of which can be modeled using graphs or matrices. In principle, we can explore different configurations to test which configuration is the most cost-effective, the most reliable, or the most profitable. However, as discussed previously, these goals can be antagonistic, and a reliable network can be not cost-effective, and vice versa. In Texas, we have experienced different events that tested the supply chain for products and power, from hurricanes to flooding due to rain from stationary tropical storms to COVID pandemia and winter storms. We have seen the product in supermarkets and the availability of electrical power dwindle, as the supply chain are designed for profitability and return on investment, but not as much on resiliency and reliability under unlikely events. Networks can be represented as graphs, directed or indirected. Graphs are composed of vertices and edges connecting them. Each edge will connect exactly two vertices. All vertices must be connected to at least another vertex in order to be considered part of the same graph. If the edges are directed, then the graph is a directed graph. In case of the directed graph, the representation includes a flow that can only travel in one direction over the edge. These graphs can be represented by matrices. There are basically two ways to use matrices to represent graphs. One is that the vertices are the columns and rows of the graph. The elements of the matrix will be the edges. In case that the graph is directed, the rows are considered to be the sources and the columns are considered to be the destinations of the flow. There is another way to use matrices to represent graphs. We can use the rows to represent vertices, and columns can be used to represent the edges. We will not include them in the current discussion. In the presentation, you can see that we have 6 source vertices labeled A, B, C, D, E, and F, and 6 destination vertices labeled 1, 2, 3, 4, 5, and 6. As you can see, the edges are directed from letter label vertices to number label vertices. The quantities are 0 for those edges that are not present in the graph. An example of what a vertex can represent would be locations. In those cases, the matrix data would represent the cost to travel from one location to another, the distance from one location to another, the time required to travel such distance. Travel could depend on factors other than distance, for instance, infrastructure or traffic jams. It can also represent the maximum capacity to move product, energy, or information through a particular channel. Another example is when the vertices can represent on one hand the different products and on the other different locations. In that case, the matrix data will represent the cost of producing or storing the product in a particular location, or the production rate of such product at that particular location. It can be a decision on whether to assign a product or not to that particular location, the demand for the product at such particular location, or the processing capability for that product at that location. We can use the case of assignment of products to explain further about mathematical notation. In this case, we see that for matrix A, if the elements that compose them A of ij represent the edges connecting products to locations, there will be in this case 6 products and 6 locations, and we can identify the 6 products simply as product 1, product 2, product 3, 4, 5, and 6. Similarly, we can represent the locations as location 1, location 2, location 3, 4, 5, and 6. You can see also there are 2 equations. These equations are constraints to control the decision-making process. In this simple example, we can constrain the model to have 1 product in each location, and each location having exactly 1 product. When you see the constraint that adds all the aij's, varying the j for each one of the i's, we are adding row-wise. That is, we fix temporarily the row I equals to 1 and add all the elements A11, A12, plus A13, plus A14, plus A15, plus A16. That total should be equal to 1. 1 represents that product I will be assigned to location J. Each product I should have 1 location J and vice versa. The symbol that looks like an inverted capital A is used to mention all I. That means that all rows will have the same way. There are some models where not all the nodes or vertices have the same constraints. In those cases, we can just write for I equals 1, 3, 4, 6, for instance. Using the same logic, we can now vary the location by adding all the corresponding products to make sure that each location has 1 product assigned. Many operations can be performed using the data in the matrices that represent our network. For instance, we can estimate the cost associated to a location-to-location matrix. Each column and each row represent a location in this example. Then, the volume represents the number of units that needs to be moved across the network from each vertex to the other vertices. If we obtain 2 matrices, one with the volume between locations and another with the distance between locations, and a cost factor to travel that network, we can obtain a total cost for each edge traveled from location to location. Also, we can obtain a grand total for that particular instance of the supply chain, in this case, $5,734.20. The total of each sale is obtained by multiplying each element with the corresponding pair ij, and all of them times the factor of dollars per mile units. Similar numerical analysis can be performed for all the supply chain network, considering all the possibilities, including facilities that currently do not exist, routes that currently do not exist, future products to be introduced to the supply chain, or new modes of transportation. Different computational tools used in industrial engineering allow us to explore multiple combinations of this solution in a smart way to find optimal design of the supply chain network. These tools include linear programming, integer programming, and mixed integer programming. There are also tools that are associated to artificial intelligence, like simulated annealing, genetic algorithms, and taboo search. The final and optimized output of the decision-making model for network design will be a subset of all the possible combinations. We will be able to optimize for different factors, including resiliency, reliability, cost-effectiveness, profitability, or return on the investment. As mentioned before, those decisions may be antagonistic with each other. However, some trade-off analysis can be performed when these goals are not perfectly aligned with each other. I hope you find this video useful. Please make comments about it. What questions would you like to ask, and if this video was helpful, to give you a good background. Thank you, and till the next one.